Here are the top 10 things you need to know about geometry. Must know number 1, angle relationships. Let's start by talking about the 3 main types of angles. First of all, an angle is the figure that's formed when you have 2 rays that share a common endpoint. So the amount of rotation to get from one of the rays to the other, represented by this yellow line here, that's the measure of the angle. And we usually measure angles in degrees. If, like drawn in this diagram, the angle is less than 90 degrees, we call that angle an acute angle. An obtuse angle is if the angle is greater than 90 degrees, and a right angle is if the angle is equal to 90 degrees. And now let's look at some relationships between different types of angles. First of all, let's look at complementary and supplementary angles. Complementary angles are angles that add up to 90 degrees. So in this diagram, let's say this angle here is angle X, this angle here is angle Y. Notice that together they form a right angle. So we'd say X and Y are complementary, and that's because if we add them together, X plus Y, it equals 90 degrees. And supplementary angles are angles that add to 180 degrees. So in this diagram, so if this is angle X and this is angle Y, notice that adding angle X and angle Y together forms a straight line. That means they must equal 180 degrees, which means they're supplementary. So in this case, X plus Y equals 180 degrees, which means X and Y are supplementary. And it's easy to recognize supplementary angles. Anytime you have angles that add up to a straight line, you know that they're supplementary, because on a straight line, there's 180 degrees. And there are a few other important angle relationships based on what are called parallel line theorems. If you have 2 parallel lines, and those lines are cut by a transversal, there are 3 different angle theorems I want to show you. The first of which is about alternate interior angles. If I zoom in a bit, what alternate interior angles are, they would be angles on opposite sides of the transversal, but inside the parallel lines. So this angle right here, we'll call that angle X, and the one on the opposite side of the transversal, but still inside the parallel lines, is over here. This is angle Y. Those are called alternate interior angles, and the alternate interior angle theorem tells us that those would be equal to each other. So I know that X and Y in this diagram are equal to each other. And often how people remember this is by drawing a Z pattern. What I've outlined in yellow looks like the letter Z. So angles inside of the Z are equal to each other. So the alternate interior angle theorem is often called the Z pattern. The next parallel line theorem is for co-interior angles. So once again, looking at angles within the parallel lines, but this time on the same side of the transversal. So for example, this angle here, we'll call that angle X, and the other interior angle on the same side of the transversal, we'll call that angle Y. These are called co-interior angles, and co-interior angles are supplementary, meaning they add to 180 degrees. So in this case, X plus Y would equal 180 degrees. And people often remember this pattern by drawing a C. So this is commonly called the C pattern. And angles inside a C add to 180. And then the last parallel line theorem is for corresponding angles. There are 2 points of intersection here for the transversal with both of the parallel lines. There's a point of intersection here and a point of intersection here. Angles at the same relative position at both of those points of intersection are going to be equal to each other. So at both of the points of intersection, if we look at the angle in the top right position for both of them, those would have to be equal to each other based on the corresponding angle theorem. And also the angle at the bottom right at each point of intersection would be equal to each other. We'll call those X and Y. And the same would be true on the other side, to the left of the transversal. As long as the angles are in the same relative position, they would have to be equal. So in this diagram, X and Y would be equal to each other because they're in the same relative position. People often remember this by drawing an F. So this is called the F pattern. Angles inside of an F are equal to each other. So those are the 3 main parallel line theorems. There's one more angle relationship I want to quickly show you, so let me make some room. The last one is if you have 2 lines that cross each other, angles opposite from each other. So let's say this angle right here, we'll call that X, and this angle right here, we'll call that Y. Angles opposite from each other are equal, and they're called vertical angles. So there's a good start for some of the main angle relationships you need in geometry. Must know number 2, properties of triangles. Let's start by looking at types of triangles based on their side length. There are three ways we can classify a triangle based on the lengths of their sides. There are equilateral, which is a triangle where all the sides are equal to each other, and all the angles are 60 degrees. So it would look like this. The second type of triangle is an isosceles triangle, and that's when only two of the sides are equal to each other, and only two of the angles are equal to each other. And here's what an isosceles triangle looks like, where two of the sides are equal, indicated by those dashes, and then the angles opposite from those equal sides are also equal to each other. And then the third type of triangle is a scalene triangle. Scalene triangles have no equal sides and no equal angles. And here's what a scalene triangle looks like, where all the sides are different lengths, indicated by these different amount of dash marks on each side, and all of the angles are different. You can also classify a triangle based on the types of angles in the triangle. An acute triangle is a triangle where all three of the angles are less than 90 degrees. So here's an example of what an acute triangle would look like. A right triangle is a triangle that has one 90-degree angle, which would look like this. And an obtuse triangle is a triangle that has one angle bigger than 90 degrees, which could look like this, where this angle right here is bigger than 90. And then the last thing I want to show you in this section are two different angle theorems for within triangles. There's the triangle angle sum theorem, which states that all the interior angles in any triangle add to 180 degrees. So in this triangle, the interior angles, let's call them x, y, and z. Even though I don't know the measure of any of the three of those angles, I know that the sum of those angles, x plus y plus z, has to be equal to 180 degrees. And the other theorem I want to show you is the exterior angle theorem, which tells us if we have a triangle, if I were to take one of the sides of the triangle and extend it, this angle here on the outside of the triangle, let's call that angle there, let's call that angle z, that angle is equal to the sum of the two opposite interior angles. So the two interior angles opposite from angle z would be these two angles here. Let's call them x and y. Based on the exterior angle theorem, I would know that x plus y would be equal to angle z. Must know number 3, congruent triangles. Congruent triangles have the exact same size and shape, and corresponding sides and angles are all exactly equal to each other. So let me give you an example of two congruent triangles. If I were to draw two congruent triangles, I can just draw any triangle to start with. I'll just draw some triangle ABC. And then to draw a triangle congruent to triangle ABC, I can just duplicate that triangle, keeping its size and shape the exact same. And I'll name that triangle DEF. Now, because those two triangles are the exact same triangle, right? They're the same size and shape, they're congruent to each other. I know that corresponding angles are all equal to each other, meaning that angle A and D are equal to each other, angle B and angle E are equal to each other, and angle C and angle F are both equal to each other. And when triangles are congruent, not only are there three pairs of angles equal, but there are three pairs of sides equal as well. BC and EF are equal, AB and DE are equal, and AC and DF are equal. And when you have two congruent triangles, I'll show you the notation to state that they're congruent. We could say triangle ABC is congruent to, and here's the notation for congruency, triangle DEF. And when I named these two triangles, I was careful to put the letters of the corresponding angles in the same position. For example, because angle A and D were equal to each other, they're both in the first position in the naming of their corresponding triangles. And next, let me show you a few tests you can do to see if two triangles are congruent. There's the side-side-side congruency test, which tells you if you have two triangles with three pairs of equivalent sides, that's enough to prove that those triangles are congruent. They must be the exact same size and shape. Another way we can tell if two triangles are congruent is the side-angle-side test for congruency. And that tells us if we have two triangles where we know there are two pairs of equivalent sides, so if those sides are equal to each other and these bottom two sides are equal to each other, and if we know the angle contained or between those two equivalent sides are equal to each other, so if this angle and this angle are equal to each other, that's enough to prove that those two triangles are congruent. And an important thing we have to know about this postulate is that the equal angles have to be between the two pairs of equivalent sides in order to know the triangles are congruent. If the equal angles were across or opposite from one of the pairs of equal sides, so let's say if they were over here in the bottom right, that would not be enough to prove that those two triangles are congruent. And then the other main test for congruency is the angle-side angle test. So if we have two triangles, where we have two pairs of equal angles, so let's say the top left in each triangle are equal, the top right in each triangle are equal, and the two triangles also have one pair of equivalent sides, let's say the top side, that's enough to prove the triangles are congruent. And for this postulate, it actually doesn't matter which pair of sides are equal, just as long as we have two pairs of angles and one pair of sides. And I'm going to show you one more quick test. It's called the hypotenuse leg test. This is a special test that only applies to right triangles. If you have two right triangles where the hypotenuses are equal and one pair of the legs are equal to each other, then we know those are congruent triangles. And let's finish this section off by doing one example where we prove two triangles are congruent. So I'll show you two triangles, triangle ABC and triangle DEF. If I zoom in on these triangles, are these triangles congruent? Well, notice side AB and DE are equal to each other. Side BC and EF are equal in length. And angle B is equal to angle E. Because we have two pairs of sides equal and one pair of angles equal, and the equal angles are contained or between the two pairs of sides that are equal to each other. So that's the side angle side test for congruency. So we know that those two triangles are in fact congruent. So triangle ABC is congruent to triangle DEF. And I know that because of the side angle side test for congruency. Must know number 4, similar triangles. Similar triangles are triangles that have the exact same shape but are different sizes. Corresponding angles are equal and ratios of corresponding sides are equal. So let's look at an example of similar triangles. Let's say I have this triangle ABC. If I duplicate this triangle and make it bigger or smaller without changing its shape, I'm only changing its size, any of these triangles are similar to triangle ABC because the angles stayed exactly the same even though the side lengths have changed. So this triangle here, let's call it triangle DEF, is similar to triangle ABC. They're the same shape, but different sizes. And I know they're the same shape because I kept all the angles equal. Angle A is equal to angle D, angle B is equal to angle E, and angle C is equal to angle F. Now, like I've been saying, I kept it the exact same shape, right? The angles are still the same, but I did change its size. So the side lengths are no longer all equal, but the ratios of corresponding sides are all going to be equal to each other. So if I find the ratio of side DE to AB, that would be the same ratio I get for each of the pairs of sides. So dividing EF by BC will give me the exact same ratio, which would be the same as the ratio of DF to AC. So the triangles are proportional to each other. And what these ratios are equal to, we call that the scale factor, which would be the number you would have to multiply any of these sides by to make it equal to the length of any of those sides. And the notation we use to demonstrate triangles are similar to each other, I could say triangle ABC is similar to triangle DEF. And now let's look at the different tests you can do to see if triangles are similar. There's angle-angle similarity, which means two triangles are similar if you have two pairs of equal angles. So if those angles are known to be equal and these angles are known to be equal, then those triangles have to be similar. They have to be the exact same shape. Or there's the side angle side test, where we would know two triangles are similar if the ratios of two pairs of sides are equal. So let's say this side is 2 and that one is 4. It's double that one. And this side is 3 and that one is 6. So notice they have the same ratio. 4 divided by 2 is 2 and 6 divided by 3 is 2. So two pairs of sides have equal ratios, and the angle between those two sides has to be the angle between those two sides is also equal. If that's true, then the triangles have to be similar. And then the last test is the side-side-side similarity test. And that's if you have two triangles that have 3 pairs of sides with equivalent ratios. So if this triangle is an equilateral triangle with all sides 3, and this one was an equilateral triangle with all sides 6, for each pair of sides, it would be 6 divided by 3, which is 2. So all the ratios would be equal. So based on that, we could say that those triangles have to be similar. So now that you know the 3 tests for testing if triangles are similar, let's look at an example where we try and prove similarity. I see 2 triangles, triangle ABC and triangle DEC. So 2 different triangles. Are they similar? Well, I know they would be similar if I can prove any one of these 3 tests. And I think I should be able to prove angle-angle similarity for this question. Based on this notation here, I can tell that side ED and AB are parallel, so I can use a parallel line theorem to show equal pairs of angles. There are 2 different pairs of alternate interior angles. Using the Z pattern, I can see that angle E and angle B would have to be equal to each other. And then using a Z pattern the other way, there's another pair of alternate interior angles. Angle A and D are also equal to each other. And then looking at C, I've got 2 lines crossing at C. So using the vertical angle theorem, I know the angles on either side of that cross would have to be equal to each other. So there's an angle C in both of the triangles, angle ECD in the top triangle and angle ACB in the bottom triangle. I'll just call it angle C in both of them. So I know those angle C's are equal to each other because of the vertical angle theorem. Showing that we have 3 pairs of equal angles is great, but we really only had to show that 2 pairs were equal. Because of some of the angles in a triangle theorem, we know that if 2 pairs are equal, all 3 would have to be equal to each other. So this is enough to be able to state that the 2 triangles are similar. I could say that triangle EDC is similar to triangle BAC. And notice I matched up the pairs of equal angles in the notation. E and B were equal to each other, so I wrote them first. D and A were equal, and then, of course, angle C's were equal. Lesson number 5, the Pythagorean theorem. In a right triangle, the sum of the squares of the shorter 2 sides, which we call the legs, equals the square of the longest side, which we call the hypotenuse. So let me help you visualize this rule. If I've got a triangle with a right angle, the shorter 2 sides of this triangle, the ones that are adjacent to the right angle, are called the legs, and we usually name those side A and side B. And the longest side, which is always the side across from the right angle, is called the hypotenuse, and I'll label that side C. And based on the Pythagorean theorem, we know the relationship between these 3 sides. In all right triangles, the sum of the squares of the shorter 2 sides, so A squared plus B squared, is always equal to the square of the longest side, the hypotenuse. So it's equal to C squared. So this is the Pythagorean theorem. And now let's do a couple examples where we use that to solve for a missing side length in a right triangle. So we have 2 examples here. Notice in both of them, I know 2 of the sides of the triangle, and I'm missing the 3rd side. Anytime you have a right angle triangle where you know 2 sides, you can use this Pythagorean theorem to solve for the 3rd side. If we look at example A, Pythagorean theorem tells us that the sum of the squares of the shorter 2 sides, so 8 squared plus 15 squared, would be equal to the square of the longest side, which is always the one across from the right angle. So it's equal to x squared. And now I can just use algebra to solve for x. If I do 64 plus 225, I get 289. And then if I want to know what value can I square to get 289, I just have to square root 289. So the value of x would be equal to the primary root of 289. And the square root of 289 is 17. So the length of side x is 17. And now let's do part B. Notice in part B, I'm missing one of the legs, whereas in part A, I was missing the hypotenuse. So it's going to work out a bit differently. Based on Pythagorean theorem, I know the sum of the squares of the shorter 2 sides, so x squared plus 8 squared, would be equal to the square of the longest side, which is always the one across from the right angle, called the hypotenuse, so it would be equal to 10 squared. And now I just have to use inverse operations to isolate the x. So I'll move the 8 squared to the other side by subtracting it. Now I have 100 minus 64, that's 36. And then if I want to solve for x, I need to figure out what number squared equals 36. The inverse of squaring is square rooting, so I can solve for x by square rooting 36. And the square root of 36 is 6. So this missing side right here, the leg, is 6 units long. Must know number 6, coordinate geometry. Coordinate geometry is great because it combines geometry and algebra together by using coordinates to describe points, lines, and shapes. So for example, let's say we have 2 points. Point A is at the point -2, 4, and point B is at the point 6, -4. So I can plot those on my Cartesian grid by using their x and y coordinates, where the x coordinate is the first coordinate of each pair, and the y coordinate is the second coordinate of each pair. And then I can use those coordinates to plot the points. To plot point A at -2, 4, I would move -2 along the x-axis and then +4 parallel to the y-axis. And that would give me the point A right here. Notice that point lines up with -2 on the x-axis and +4 on the y-axis, matching its coordinates. And then I'll do the same thing for point B. And now let's do a few questions that involve these points. Part A says to construct the line segment AB. That's what that notation means. So I'll just connect point A and point B with a straight line. Part B says to calculate the midpoint of line segment AB. So I have to figure out what point divides that segment exactly in half. Well, let me show you the formula for calculating the midpoint of a line segment. Notice the formula gives us a point that has a new x and a new y coordinate. To get the x coordinate of the midpoint, we're basically just finding the average of the two x coordinates of the endpoints. We add x1 and x2, and then divide the sum by 2. That finds the average of them. And then do the same thing for the y's, find the average of the y coordinates. Notice in this formula, you see a lot of subscripts 1s and 2s with the x's and y's. That's just a way of coding the x's and y's between two different points that you have. So if we call point A our first point, we'd say that its coordinates are our first x and our first y, and then if point B is our second point, that's our x2, y2. So then how this formula works is it finds you the midpoint. It finds you the x and y coordinates of the middle of the line segment by taking the average of the two x coordinates that we have, right? By adding them and dividing by 2, that's finding the middle, or the average of the two of them. And then the same thing for the y coordinates. Add them and divide by 2 finds you the middle, or average, of those. So if I sub all of these values into this formula, the x coordinate is -2 plus 6, which is 4, divided by 2 is 2. And then the y coordinate, 4 plus -4 is 0, divided by 2 is 0. So the midpoint is at the point 2, 0. Notice if I plot that point 2, 0, that's right in the middle of the line segment. It cuts the line segment exactly in half. The length from A to the midpoint and the midpoint to B would be exactly equal to each other. And speaking of length, that brings us to our next example. Let's do part C, where we actually calculate the length of the line segment. The formula for calculating the length of a line segment looks like this. Let me zoom in on it a bit. To find the length of a line segment, you find the difference in the x coordinates squared, the difference in the y coordinates squared, add those results together, and then square root it. After we go through finding the length, I'll show you why this formula works. So using this formula, I have to take these coordinates and sub them in for the proper variables. And then simplifying underneath the square root, that simplifies to 8, and that simplifies to -8, and when squaring them both, they're both 64. Adding them together is 128, so I have the length of the line is the square root of 128. And that can be simplified. It can be broken up into root 64 root 2, which is just 8 root 2, which has an approximate value of about 11.3. And when using this formula, really what we're doing is just Pythagorean theorem, what we looked at in a previous section. If I were to turn this line segment into a right triangle, the length of these two sides would both be 8. And in the formula, when we find the difference in the x's, that's what we're figuring out. What's the horizontal distance between the 2 points? It's 8. And same thing with the difference in the y's, that's the vertical distance. Now I know this is -8, but that's fine. When we end up squaring the difference, it doesn't matter. And then Pythagorean theorem, remember, tells us that the sum of the squares of the shorter two sides equals the square of the longer side. So if we subbed into Pythagorean theorem those for the legs and then solved for the hypotenuse, we would get exactly this, 8 root 2, or approximately 11.3. Let's know number 7, circles. Let's go over some basic terminology with circles. If I've got this circle, and I put a point at the center. The radius of the circle would be a line that goes from the center of the circle to the edge of the circle. So if I start at the center and go anywhere to the edge, that represents the radius of the circle. And by the definition of the circle, every point around the outside of it is equal distance from the center. So it wouldn't matter where along the edge you drew the radius to, as long as you start at the center and go to the edge, it's going to be the exact same length, and we call that length the radius. Next is the diameter. A diameter of the circle connects 2 points on the circle, and it goes through the center. So if I start along the edge of the circle, go through the center all the way across to a point on the other side, that line is called the diameter. And next, I'll draw a chord, which is a line that has both its endpoints on the circle. But a chord does not have to go through the center. So a chord could look like this. Both its endpoints lay on the circle. And next, I'll draw a tangent. A tangent line is a line that touches the circle at exactly 1 point. So it doesn't go through the circle, it just touches it at a single point. So if I were to draw a point on the edge of the circle right here, a line tangent to the circle at that point would look like this. Notice this line, if it continued forever in both directions, it would never touch the circle at any other points. And lastly is the arc of a circle. An arc is just a portion of the circle's circumference. So if I outlined this area here, that represents a portion of the circle's circumference. We call that an arc length. And now that we've gone over some of the basic terminology, let me show you 3 basic angle relationships that you should know in circles. The first angle relationship you should know is that angles within the same segment are equal to each other. Let me show you what this means. If we have some chord on this circle, and now I'm going to draw 2 angles on the circumference of the circle subtended by this chord. So I'll draw angle X, and I'll also draw angle Y. Because both angle X and angle Y are both subtended by the same chord, and they're both on the same side of that chord, so they're within the same segment, then I know those 2 angles have to be equal to each other. So in this rule, I can state that angle X is equal to angle Y. And the next angle relationship I want to show you is that the central angle of a circle is double the angle at the circumference. And let me show you what that looks like. So once again, if I have a chord, if I were to draw an angle subtended by this chord that goes to the circumference of the circle, I'll call it angle X. And then if I were to also draw an angle subtended by the same chord that goes to the center of the circle, the angle at the center of the circle is exactly equal to double the angle at the circumference of the circle. So I could label it 2x. And once again, notice for this rule to work, both of the angles, the one at the circumference and the one at the middle, have to be on the same side of the chord. They have to be in the same segment. And now let me make a bit of room and show you one more angle relationship. And the last relationship that I want to show you says that the angle formed by the tangent and a chord is exactly equal to the angle in the opposite segment. So I'll show you what that looks like. If I pick some point on the circumference of this circle, draw a tangent at that point, and now draw a chord of the circle that starts at that exact same point, the chord can go to anywhere. The angle between that chord and that tangent, which I'll outline in blue here, which I'm doing right now, is going to be exactly equal to any angle subtended by this same chord in the segment opposite from where this outlined angle is. So for example, it could be to over here along the circumference, as long as it's subtended by that same chord. So this angle right here and this angle right here are exactly equal to each other. And it wouldn't have mattered where along this portion of the circumference I drew this angle, because I know they'd all be equal to each other. And any of those angles is equal to the angle between the chord and the tangent on the opposite side of the chord. So there's a quick look at the entire circle section. Must know number 8, area and perimeter. Let's start by looking at area. Area is simply put just the amount of space inside a 2D shape. And there are different formulas to find the area of different shapes, but let me show you a couple. Let's start with the rectangle. To find an area of a rectangle, you do its length times its width. So in the rectangle that I've drawn, its length is 8 and its width is 4. And it doesn't matter which one is length and which one is width, because the order of multiplication doesn't matter. So when I do length times width, I do 8 centimeters times 4 centimeters. 8 times 4 is 32. And because I have centimeters times centimeters, I end up with my units for the area being centimeters squared. And another common shape that you should definitely know how to find the area of is a circle. If I zoom in on this circle, to find the area of any circle, you just do pi times the radius squared. Well, the radius is just the distance from the center to the edge of the circle. And I can see in the diagram that my radius is 3 inches. So my area would be pi times 3 inches squared. That gives me, 3 squared is 9, so it gives me 9 pi inches squared. Area, the units are always squared for area. And now let's take a look at perimeter. So we'll look at those same two shapes. Starting with the rectangle, if I want the distance around the outside of the rectangle, I just have to add up all of their side lengths. But notice, these two sides are exactly equal to each other, and these two sides are exactly equal to each other. So what I could do for my formula for the perimeter of a rectangle, I can just do 2 times the length plus 2 times the width. So that would equal 2 times 8 plus 2 times 4. Because there are 2 sides that are 8 and 2 sides that are 4. That gives me 16 plus 8, which is 24 centimeters. And for the circle, the perimeter of a circle, there's actually a special name for it. It's called the circumference. And to calculate the circumference of a circle, you do 2 times pi times r, or you can just do pi times d, because 2 times the radius is equal to the diameter. Since in the diagram I'm given the radius, I'll use this version of the circumference formula. The circumference would equal 2 times pi times 3, which is 6 pi. And once again, if I want an exact answer, I'll leave it like that. So 6 pi inches is the circumference of that circle. Must know number 9, surface area and volume. Let's start with surface area. Surface area is the total area of all the outer faces of a 3D object. Let's start by looking at a rectangular prism. This rectangular prism has 3 dimensions: a length, a width, and a height. The formula for a surface area of a rectangular prism is 2 times the length times the width, plus 2 times the length times the height, plus 2 times the width times the height. And so you understand how this works, let's just take a look at this first part of the formula, 2 times length times width. Well, if I do the length times the width, that finds me the area of the bottom of this rectangular prism. And the reason why I have a 2 in front is because the top of the rectangular prism is the exact same area as the bottom, which is why we double it. That finds us the area of the top and bottom. When we do 2 times length times height, that finds us the area of the front and the back of the rectangular prism. And 2 width height finds us the area of the right side and the left side. And now if I sub into this formula, if I find the products, I have 12 plus 24 plus 36. That would be 72 units squared. In the diagram, the dimensions didn't have units, so I'll just write units squared. Surface area, whenever we're doing any type of area, the units are always going to be squared in our final answer. And now let's do one more shape for surface area. Let's do a cylinder. If I zoom in on this diagram of the cylinder, let's look at how we can find its surface area. To find the surface area, I need to find the area of all the outer faces. So the surface area would equal, well, I need the area of the top and the bottom of the cylinder, and those are both circles. And to find the area of a circle, you do pi r squared. So I'll have to do pi r squared, right? That's the area of the top, and then multiply it by 2 because the bottom is the exact same area as the top. And then to the area of the top and bottom, I have to add the area of the lateral surface, which is like the side of the cylinder. And if we were to imagine unrolling this cylinder into its net, you would see that that lateral surface is actually a rectangle. And to find the area of a rectangle, you just do its length times its width. Well, the length of the rectangle, once the cylinder is unrolled, the length is equal to the circumference of the circle. And circumference of a circle is 2 pi r. And then that gets multiplied by the width of the rectangle, which would just be whatever the height of the can was. So 2 pi r times h will find the area of the lateral surface. So I'll add 2 pi r h. And then if I sub into this formula, if I simplify, I get 50 pi plus 90 pi. Collecting those together, that's 140 pi units squared, right? Surface area is an area, it's units squared. And now let's also take a look at volume. Volume is the amount of space inside a 3D object. And for prisms, if you want to find the volume, you follow the formula, area of base times height. So let's look at those same two shapes and let's find their volumes. For the rectangular prism, if I want the volume, I have to do the area of its base. So the area of the bottom rectangle will be length times width. So I'll do length times width, and then you have to multiply that by the height, so times h. So if I sub into the formula, it's just 2 times 3 times 6. That's 36 units, and for volume, it's always units cubed, because we're multiplying 3 dimensions together, and each of those dimensions have a unit, so we get units cubed for volume. And for a cylinder, if I want its volume, well, a cylinder, let me zoom in a bit here again. A cylinder is a type of prism where the base is a circle. So to find the volume, I need the area of the base, which is pi r squared, then that gets multiplied by the height. So pi r squared h finds you the volume of a cylinder. If I sub into this formula, I get pi times 5 squared times 9, which is 225 pi units cubed. So that's a good start for surface area and volume. Remember, for different shapes, there are different formulas to find their surface areas and their volumes, but the general idea stays the same. Must know number 10, transformations. A transformation is a change applied to a geometric figure that moves, resizes, or flips it on a coordinate plane. So if we have some triangle ABC with the following coordinates, let's look at 3 of the main types of transformations that you might see. Translations, which is just sliding a shape. Dilations, which means to resize a shape. And reflections, which means to flip a shape. Before we do any of these transformations, why don't I graph that triangle ABC on these grids below? If we start with translations, let me zoom in on that section. Translation just means to slide a shape left, right, up, or down. And it's going to be communicated like this. A translation of A, comma, B, where the A tells you how much it's going to shift left or right, and the B shifts it up or down. So what we do to perform those transformations is we take the pre-image points, so the points of the shape before it's transformed. The pre-image point would be x, y, and then we get the image points of our translated shape by adding the A value to x and adding the B value to y. So the image point becomes x plus A, comma, y plus b. So let's apply the transformation 1, negative 4 to triangle ABC. So I need to get my image points, which we call A prime, B prime, and C prime. So I can start by taking my points A, B, and C. And notice I left a lot of spaces when I wrote the coordinates because what I need to do is to each of the x coordinates, I need to add 1, and to each of the y coordinates, I need to subtract 4. And that would give me the point A prime as 2, negative 3. B prime would be 5, negative 3. And C prime would be 3, 0. And then if I plot those points on my grid, and then connect to form the triangle, we get our translated triangle. All of the points that make up this shape have all just been shifted 1 unit to the right, and then 4 units down. And now let's do a dilation. If some point xy undergoes a dilation centered at the origin by a factor of k, then the image point, p prime, just becomes k times x and k times y. And it's important to note this only works if the dilation is centered at the origin. So let's apply a dilation by a scale factor of 2 centered at the origin. So to get my image points, I just have to take all of my original points and multiply both the x's and the y's all by 2. So if a was 1, 1, a prime would become 2, 2. Double the x and double the y. And do that for all of them. Instead of 4, 1, it becomes 8, 2. And instead of 2, 4, it becomes 4, 8. So if I plot all those points, you'll see what a dilation looks like. There's my transformed triangle. Let me zoom in on it so you can see how it works. Every single point's distance from the origin has doubled, and that's because the dilation was centered at the origin. So if we look at the relationship between these 2 points, notice the yellow one is twice as far from the origin as the original point was. And that's true for every pair of points. Looking at these two, the image point, the transformed point, is twice as far from the origin as the original point was. And now lastly, let's look at reflections. If we have some pre-image point A, and I want to reflect it across some line, point A prime will be on the other side of that line in such a way that that line is the right bisector of the line connecting A and A prime together, meaning it goes right through the middle of that connecting line and it goes through it at a 90-degree angle. And there's a few general rules for how we can flip points across different lines. If we want to do a reflection across the x-axis, point xy, if that's our pre-image point, when we reflect it across the x-axis, we get p prime x negative y. So just the sign of the y-coordinate has to change. And if we reflect across the y-axis, we take point xy and just change the sign of its x-coordinate. So p prime becomes negative x, y. And if we wanted to reflect across the diagonal line y equals x, we just take our point xy and switch the x and y coordinates. So the image point becomes yx. So for this triangle here, why don't we perform a horizontal reflection across the y-axis? So when reflecting across the y-axis, I'll need to get my image points A prime, B prime, and C prime. When reflecting across the y-axis, this axis here, if that's my line of reflection, I can do that just by changing the sign of all the x-coordinates. Right? We wrote that rule here. Across the y-axis, all points xy change to p prime negative xy. So just change the sign of all the x's. So I'm going to rewrite these points, but the x-coordinates are all going to change signs. So instead of 1, 4, and 2, they're going to be negative 1, negative 4, and negative 2. The y-coordinates will stay exactly the same though. And now if I plot those points, I get a triangle that has been perfectly reflected across the y-axis. So those are the main transformations that you'll see. Hopefully this video helped you with geometry. Make sure to leave a comment about what you want a top 10 of next.
Jensen Man!